So let's go ahead and begin. So welcome everyone to TTP 211. So this is our Energy and Transportation Systems Modeling course. Hopefully you guys are all in the right place. So we're going to start off with some quick course logistics. Okay, so my office hours are going to be on Mondays from 10 to 11 at my office in Gaussy. If you're not able to make that time but want to meet, you can always shoot me an email. Always happy to schedule a different time if needed. And then our TA for the quarter is going to be Grant, and he will be holding his office hours on Tuesdays 2 to 3 over in West Village. All right. Okay, so grading. I don't know if folks have had a chance to look at the syllabus yet. All of that information is available on Canvas. So this is kind of just a repeat of that. But so class participation, this is a little bit more hand wavy. It counts both attendance and participation. Basically, I'm not gonna check off everyone who's here every day, but if you're missing a lot and you're kind of right on the border, right, this can make a difference for your grade. Otherwise, I wouldn't kind of worry about it too much. The majority of the grade is going to be based on the homeworks. And so the homeworks, there's going to be 4 total throughout the quarter. And yeah, there's going to be a 10% penalty per day. And then last piece of it is the final project. And I'll talk more about this in just a second. So that's a little more than a third of the grade. And that's divided into 3 pieces: our proposal, final presentation, and a project report. So you can work in groups for the final project. We've had some years where almost everyone in the class ended up doing it on their own. We've had some years where everyone was in a group, so kind of up to you guys to decide. The due dates for these project components are already up on Canvas, and so there's a rubric as well, and you can check that in the class materials. Project proposal is due February 16th, so that's like a 1 to 2 page proposal. It's basically to make sure that you guys are starting to think about the final project and developing ideas for it, like not so last minute. Okay, and then class presentations. So we'll have the last week of classes before finals is just going to be you guys presenting your final projects, which means that the presentations is due on the first day so that everyone has kind of the same amount of time, right? And so Monday and Wednesday, all the presentations will be due on Monday at the start of class. And then project report, I say roughly 8 to 10 pages, but I'm not really paying attention to the page limits. If it needs to be longer, that's fine. Okay, any questions about any of this so far? Okay, last bit. So next week, I am in a conference in DC, and so I'm going to pre-record the lectures and put them up on YouTube, so you guys can watch them whenever you want, as long as you do it before our subsequent class the week after that. Which actually, the week after that, the Monday, is a holiday, so we won't be meeting then. So you guys have like a week and a half off after this week. And then really, as a quick aside, who here is taking my other class, my 298 class? Okay, so for the folks who are taking that class, there's actually a lot of overlapping material in the first 2 weeks. So lectures 2 and 3 of this class, you guys don't need to attend because there will be overlapped material, if that makes sense. Okay, I'll post that on Canvas just to make sure everyone gets that message. Okay, any questions about course logistics? Alrighty. So I guess we'll dive straight into it then. So quick kind of introduction to what we're going to be talking about in this course. All right, so what is an energy system? So these are all the components that are related to the production, conversion, delivery, and use of energy. And so you guys have probably been taking classes or have taken classes that talk about maybe specific elements of these in more detail, and we will cover specific elements of these as well. But that sort of idea is to think of them together holistically in a single sort of system. And so we're going to be, the concept of this class is going to be talking about sort of each of these and building them up so that we have the foundation to actually understand what goes into an energy system. We're also going to be learning kind of techniques and methods that folks often use to sort of model a variety of these things in an interrelated way. Okay, so we want to understand, so why do we do sort of these energy modeling of our systems? So to understand energy consumption and associated impacts. So we might think of a number of these things that we might be interested in, but in order to really have a holistic understanding of any individual pieces of these, you kind of have to understand how it affects the whole system, right? So technology adoption, fuel consumption, cost and price, so economics, and then environmental impact. So the main things that we'll be talking about are greenhouse gas emissions and criteria pollutant emissions. There are other impacts that are there, but that we don't cover as much in this particular course. And we're going to be deriving sort of expertise from across a number of different sort of topical and methodological disciplines. So energy, engineering, environment, economics. The sort of high-level architecture of our energy system, you can think of in a really sort of simplified way, broken down like this. So we have the way that I've divided it here is by sort of energy type. So primary energy, secondary energy, final energy, and then the services that they provide. And we'll talk a little bit more about specifically what that means later on today. But this is a sort of quick and dirty way of thinking about our energy system. And the first 2 weeks, we're mainly going to be thinking about the first and sort of second box, as well as sort of details associated with our sort of primary energy and how that gets to become secondary energy. So we'll talk about extraction and treatment of fuels and conversion of those fuels into secondary energy. Most of those are going to be producing things that I think you guys are familiar with, right? So like electricity and gasoline that are providing a lot of the services that we'll end up talking about a little bit later. And then one thing that I want to, distribution as well. One thing that I want to highlight is the sort of application of the system models, right? And so a lot of, I would say, like the first 2/3 of class is really focused on developing our skill set to both understand the topical nature of these as well as methods to actually do the modeling. But then the last bit of the class, we're going to be thinking about impacts and how that's often affiliated with policy. And so we're going to look at a bunch of sort of case studies on applications of systems models that have helped to shape policy decisions. All right. Any questions about this? Yes?
I guess, are you going to be talking also about the waste disposal regulations in regards to the energy process as well?
Yeah, so that's not currently in the list of policy case studies at the end, but if you're interested, I would be happy to, add that in, and we can put that into, I think the third to last lecture is going to be a good spot for that, actually. So remind me, and I will make it happen. And if anyone else is interested in particular topics, I'm happy to kind of shape the policy content at the end to explore things that folks are interested in, because I want this to be useful for you guys. Yeah.
I was kind of curious about, are we going to look at like the transportation of possibly like food, and as that applies to policy, or like as?
So there is one piece that we do a deeper dive into with LCFS that touches on a lot of like kind of fringe food, fuel trade-off, food fuel trade-off things that were actually very controversial like 20 years ago and still actually continue to be a little bit debated. So a little bit of that. If there are more specific things that you're looking for, you can, let me know. Yeah, and so this is basically what I was just mentioning. What's the impact of specific policy changes to a system? So that's actually one piece of it, right? So as, let's say, Congress or a governor or a local legislature creates a policy that impacts our energy system, one of the things we want to do is be able to understand how that policy is going to impact that system. And so we'll develop the skill sets for that, but also the other piece of that is relevant is that also we want to be able to use our knowledge and models to create good policy, right? And not just evaluate the impacts of specific policies. And so we should be developing, scenarios in our models to examine the effects of potential future policies as well. Okay, and so the general schema, as I've been kind of describing, background is building knowledge of the basic sort of engineering and technology pieces, and so we'll spend the first 2 weeks going through that, and then we'll do probably the bulk of the class on developing skill sets, tools that people use to employ in the development of sort of these larger scale system models. And so we're not necessarily doing a deep dive into any one particular energy system models, because of which there are many that exist, but rather the skills that you develop in this course hopefully will allow you to kind of understand the general workings of any particular sort of system model. We will take a look at a high level of a number of different sort of system models that already exist today. Some of the more popular ones. We'll be focusing mainly on energy systems models in the beginning, but then we'll expand kind of at the end to look at some integrated assessment models, which are larger scale models that include the energy system as a component, but might include other things as well, right? So like it might be a coupled energy system and climate model. And so the integrated assessment models are kind of these broader body of models that are kind of a larger in scope. And we'll do kind of a high level look at them kind of later on in the class. And then lastly, the policy case studies, we're going to look at a number of different places where these models are applied and how they've informed different sort of policy actions and decisions. Okay. Any questions? All right, so that's kind of our quick overview. And now, so the thing about this class is, we're drawing folks from a number of different disciplines. So who here is like more engineering based? and then who here is more like social science-y, couple people, yeah, right. And so, yeah, so we're gonna do kind of a quick foundational physics recap, just so that we can be kind of on the same page. Some of this is going to be probably a little bit simpler for the folks who are a little bit more familiar in the sort of engineering space. But we got to lay our groundwork, right? So, what is energy? Right, we're going to start at the very basics. So, energy is the ability to perform work, which means moving something or to heat an object. There's a bunch of different forms of energy. So kinetic, chemical, heat, electrical, electromagnetic, elastic, nuclear, gravitational. We're mainly going to be talking about the first four. Okay, the other ones are at scales that we're not really going to be thinking about too much. Okay. Conservation of energy versus energy conservation. There's like a couple of these things that I'm just gonna highlight because we can get a little bit nitpicky about this, right? So conservation of energy is from a physics concept, specifically thinking about how energy can't be created or destroyed. We're just converting energy from one form to another. But then when I'm usually talking about energy conservation here, in this class, it's more of a sustainability concept where we are reducing energy usage to prevent wasting of energy. I'll also note that this idea of conservation of energy, where you have heat, kinetic, electrical to heat, that doesn't tell us about the sort of usefulness of different forms of energy, of which in this particular class, when we're thinking about energy systems, that'll be important to think about because certain forms of energy are going to be more useful than others because the way in which we extract services or useful work from certain forms of energy is going to be different depending on the sort of type of energy. Okay, so how is energy measured? So there are lots of different units of energy. So joules, watt hours, British thermal units, which are BTUs, calories, and then electron volts. Joules, so we'll talk a little bit more specifically about each of these. EV, electron volts, is probably the only one that we are not really going to talk about. That's like thinking about energy at the atomic level, which we're not going to deal with here. So we'll go through each of these. So joule is the gold standard. It's the SI unit for energy, and it's used across a whole wide variety of applications and fields. Does anyone know actually what a joule represents? Any ideas? Thinking back to probably chemistry in high school. Yeah.
The amount of energy to raise a specific volume of water in degrees Celsius.
Yes, that's right. So that's the one that they talk about in chemistry. So heating 1 gram of water by 0.24 degrees Celsius. But actually the more sort of standard application of the joule is the ability to move 1 kilogram of mass a distance of 1 meter with a certain acceleration, 1 meter per second squared. Yeah, and so hopefully you guys are all sort of generally familiar with this. This is a unit of energy, or energy can be described kind of universally in joules. It's the standard and most sort of, I would argue, yeah, the most recognizable. The other big one that we're going to be talking about are watt hours. And this is most commonly used in electricity. Okay, and so a watt is actually a unit of power. We'll talk about power in just a moment. But this is the amount of energy used at a constant power rate over a period of time. And so a watt is a joule, is 1 joule per second. And so where do you guys think we get this 3.6 kilojoules from for 1 watt hour? What do you guys think? Time, what does that mean?
There's 60 minutes in an hour and 60 seconds in minutes, and then you multiply that, you get to 1,600.
Yeah, so very simply, if it's 1 watt dash hour, this is equal to 1 joule per second times hour. And then I just need to do a unit conversion here, right? So this is equal to 1 joule per second, and there's 60 seconds in a minute, and there's 60 minutes per hour, right? And that's where I get 3,600 joules. So it really, when we say watt hour, it's literally a watt times an hour, and then you do a set of sort of unit conversion. So 3.6 kilojoules or 3,600 joules. So that's kind of the standard way that you can convert between a watt hour and a units of joules. And so why is it that we use watt hours, and why is that so commonly used in electricity? Well, it's very convenient, right? So when you measure electricity consumption specifically, you can think of it in terms of consumption by hour, and so it's easily kind of reported in this way. So if you think of, this is kind of like an old school meter, right? But you can go and read this and say, oh, how many kilowatt hours were consumed? It just tells you the amount of energy based on the wattage over the period of time that's used. And so most commonly at the residential level, we're thinking about things in kilowatt hours. And then in larger contexts, like if you're thinking about like power plants, you're often talking about things in megawatt hours, gigawatt hours, terawatt hours. Okay? Any questions? All right, moving on. BTUs. Where do we use BTUs? Any ideas?
Air conditioning.
Yeah, air conditioning. Yeah, that is one of the common ones. The other one, yeah, fuels. So oftentimes used to measure the energy content of fuels. A BTU is kind of like a joule, but imperial version. So this is the amount of energy used to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So you can think of it as like the kind of like an imperial version of a joule. So 1 BTU is roughly 1,000 joules. And in the context of our class, probably the most common place that we'll see it, although we don't really use BTUs that much, is natural gas. So an MMBTU is 1,000,000 BTUs. So that's a very common way to see it being displayed as an MMBTU. And 1,000 cubic feet of natural gas is about 1 MMBTU. And then there's this sort of odd unit called a therm, which is actually just 100,000 BTUs. So 100 cubic feet of natural gas is about 1 therm. Yeah, I wouldn't worry too much about this one. Again, we won't use it very often. And then from a scale perspective, the last one to know, just so that for context, if you see it, a quad, and a quad is a quadrillion BTU, and we think of this in the scale context of like a large scale economy. So you can think of like the amount of energy consumption of like the United States would be some number of quads. Okay. Last one to talk about, energy units for food. I think most people are pretty familiar with this. This is similar to BTUs actually, except that it uses units in metric. So 1 calorie is the energy required to raise the temperature of 1 gram of water by 1 degree Celsius at 1 atmosphere. And so if you remember, a joule is the same thing except it's 0.24, right? And so 0.24 degrees Celsius. So roughly 1 calorie is about 4 joules. Okay, so everyone's seen a nutrition fact label before? Yeah. So this says 25 calories. So how many joules would that be? About 100. It's actually 100,000 because calories in food labels are actually kilocalories. But that's like, they don't tell you that. So don't think that you can eat this whole, whatever this is, maybe it's like Pringles or something. You can't eat that whole thing and only get 100 joules worth. It's actually 100,000 joules. Okay, so we're gonna do a kind of quick little game here. So can you guess the energy content? Okay, and so this will be a little bit of an exercise in orders of magnitude as well. So you guys just need to guess like between 1 to 10, 10 to 100, 100 to 1,000, 1,000 to 10,000, and so on. And you can do whatever units that you want if you're more commonly used to thinking of it in calories, joules, kilowatt hours, whatever. So just yell it out, I guess. What do you guys think? So average meal, how much energy is in an average meal?
600 calories.
So calories, so we're saying 100 to 1,000, 100 to 1,000 calories, which are kilocalories, right? That's right. And so that's going to be on the order of, so when we switch to joules, it's going to be kind of the same units because 4 is in the same order of magnitude. So we're going to say 100 to 1,000 kilojoules. Okay, how much energy do you think is in the human body? 100 meals. So it'll be 100 times 100. So 10 to the 4th to 10 to the 5th kilojoules is what you're saying. Anyone think it's more or less?
It's gotta be more.
It's more?
Yeah.
100 to 1,000 megajoules. So I think you're off by 1 order of magnitude. But close, yeah. Yeah, so actually, quick aside, does anyone know how you actually measure the energy content of food when we talk about like calories? Yeah, you put it in a bomb calorimeter, right? So if you put a human in a bomb calorimeter, you would get something like this, right? Okay, what about 1 kilogram of coal? How much energy do you think? So you can think of this, relative to what you might find in like the human body, right? Would we say kind of more or less? Less? Okay. Yeah, that's right. So we'll say 1 order of magnitude less, so 10 to 100 megajoules. It's kind of like middle of that. What about a gallon of gas compared to 1 kilogram of coal?
Diesel or?
I mean,
It doesn't matter.
yeah, it won't matter from orders of magnitude. Yeah, so this is actually kind of at the upper end of that. So about 100 megajoules, 100,000 BTUs. Okay. So those are kind of our traditional fossil fuels, right? And so now we think about let's say, energy content of, if I wanted to start thinking about something like solar, if I had a 1 meter squared and you had sun shining on that particular area of land for 1 hour, how much energy is kind of hitting the ground? What do you guys think? 1 kilowatt hour? Okay, so that would be 3.6 times 10 to the 6th joules. So you're saying about 1 million to 10 million joules. Yeah, that's right. So, you know, I was alluding to kind of solar power, but note that, right, that's not thinking about efficiency and conversion losses or anything. So strictly speaking, you probably would need like 10 meters squared for an hour of just pure sunlight to equate to getting on the same order of magnitude as coal. Okay. Okay, what about the energy content of an EV battery? What do you guys think? Yeah. So 10 to 100 kilowatt hours, so 100 to 1,000 megajoules. Yeah, and so you can start to contextualize maybe some of the sort of issues here, right? So gallon of gas, that might be equivalent to like a really small battery, and then for a full-size battery you might need something like 10 gallons of gas, right, to be equal in the sort of energy content. Okay, how much energy does a house use in a day? Any ideas? Yeah. So the average consumption, I think that most people cite is about the average power consumption is about 1 kilowatt, and then over a whole day, 24 hours, you're talking on the order of like 20 to 30 kilowatt hours, right? So we're in the 10 to 100 kilowatt hour range. Okay, and just for fun, we're gonna jump way up here. How much energy is in a nuclear explosion? You get fake bonus points if you get within, let's say, an order of magnitude. A billion megajoules. All right, 10 to the 9th megajoules. Well done. So depends on the nuclear bomb, but yeah, 10 to 100 times 10 to the 9th, which means you're powering something like 1 million. You can power like 1 million houses for a day with a nuclear bomb, or sorry, a billion or 100 million to 1 billion houses. U.S. annual consumption is about 100 exajoules or 100 quads. As I was mentioning, that's kind of the units that we use for economy scales if you don't want to use joules for some reason. Okay, and so given that, what do you guys think the world annual consumption would be? Yeah, so it's about 100,000 terawatt hours. So we're kind of an order of magnitude larger than the US if you add everything up in total. Okay? Any questions about any of this? We'll do a similar thing for power in a second. Okay, so this one's a little bit older, I guess, 2021, but this gives a breakdown of kind of the energy consumption by fuel type on the left, and then it gets kind of allocated into end-use sectors on the right, which you can see kind of broken down here, right? And so where is our energy coming from, right? It's a third in petroleum, a third in natural gas, and then the rest of it kind of broken down into renewables, coal, and nuclear. And I should say that renewable energy figure does include things like hydropower, right, which is actually going to be a much larger percentage of that pie compared to, I think most people are thinking wind and solar for renewables. Okay, and then there is kind of this intermediary where we can see which of these input fuels are going to initially create electricity that goes into our end uses. So you can see how much of each of these are used to make electricity. And then the way that we use it is about 40% in transportation, 35% industrial, and then the remaining kind of split between residential and commercial. Okay. So that's really high level sort of overview of US energy consumption, and then we're going to get a lot more into detail on kind of the left half in the first couple weeks. Okay, the next piece is thinking about power. So energy and power are not the same thing. Power is the rate at which I do work, right? So energy is the thing in which I can measure how much work can be done, and power is the thing that lets me measure how the rate at which work can be done. So energy divided by time. So the main two units of power that we'll be talking about are watts and horsepower. Okay, so similar to a joule, right? The SI unit for power is a watt. So 1 watt is equal to 1 joule per second. Most commonly used so I shouldn't say most commonly used. Watt is the most common application of power. It's commonly used in electricity to describe capacities of like power plants, right? And so if a plant has an installed capacity of 10 megawatts, that's not speaking to the amount of energy that it's producing directly. It is the capability of that power plant to like physically produce something like 10 megawatts of instantaneous power. Okay. And then the other one, horsepower. I'm sure you guys have all heard of this, right? So this is often used to describe power for engines and for other sort of mechanical power. For energy, we talked about like what it actually means, in terms of like the amount of energy needed to heat water. There is an equivalent for horsepower. Does anyone know what that is? So it is the ability to lift 75 kilograms 1 meter in 1 second. Okay, and so unfortunately, there's actually slightly different definitions of horsepower. There is an imperial version of horsepower, which is 745.7 watts equivalent. There's also a metric one that is very close, 735.5 watts. So just so that you guys know, there is a slight difference in the terminology of horsepower. We won't really be dealing with horsepower too much, so you won't need to worry too much about this, but just for your edification. Okay, does anyone know what the peak power production of a horse is? No, it's about 15. So, yeah. So, the joke is that a horse can produce a lot more horsepower than one horse, but that's actually the peak power production. The term horsepower comes from the sort of average power that a certain type of horse produces, which is about 1. But yeah, not at the peak. Okay, so we'll do a similar little exercise here. Can you guess the power?
Is that
Yeah. So light bulbs. What do you guys think? Yeah. So if I asked this question like 15 years ago, the answer would actually be pretty different depending on the type of light bulb. The efficiency of light bulbs has like drastically improved because actually for a lot of it can be attributed to policy reasons during the Obama era with the Department of Energy requirements for lighting. So if we're talking about incandescent light bulbs, which are the old ones that used to get hot, right? Those might be on the 10 to 100 watts. But today, we're probably more on the order of like 1 to 10 watts if you're using LEDs. Okay. Okay. How much power does a human exercising produce? What do you guys think? Or use, I should say. So 300, yeah, so we would be saying 100 to 1,000 watts. 300 would be pretty high. There's actually these cool videos of like competitive bicyclists who try to power a toaster, right? And they can do that for like 30 seconds tops, right? Because the amount of wattage to do something like that is actually probably substantially higher than a human could sustain. So yeah, but order of magnitude 100 to 1,000, but I put a smaller range here just so we're not kind of confusing people that it's more on the lower end of that. Okay, what about your microwave at home? Anyone have any ideas? Yeah, that's right, about 1,000 watts. Okay, so solar panel on, so let's say a typical sort of solar panel, how much power would that produce?
Depends on the size.
Yeah, so something like, I think there are like 2 meters squared ish, 1 to 2 meters squared. Yeah, so on the order of 100 to 1,000 watts when we're talking about order of magnitude, but to be a little bit more specific, your typical panel is kind of in the area of like 250 to 350 watts, depending on its characteristics, and the newer ones are able to get a slightly more. And then when you think about like a utility scale, sort of like the large solar plants, so large arrays of solar panels like out in the desert, you're talking about on the order of I would say actually 10 to 1,000 megawatts, depending on kind of the size. 1,000 or 1 gigawatt would be a very large, sort of substantial field. Okay, household, we talked about this already, about 1 kilowatt, right? Okay, car engine, what do you guys think? Yeah, so you're saying 200 horsepower, so on the order of 100 to 1,000, and in fact there are some cars that I think actually have, there's one car that has like 1,000 horsepower. And then we're kind of in the same order of magnitude with kilowatts, so 100 to 1,000 kilowatts. Okay, what about wind turbines? What do you guys think? 1 big wind turbine.
1 megawatt.
Yeah, that's right. So, yeah, we're saying 1 to 10. So 1 megawatt is kind of the standard one that you would think of. The sort of big ones that you might see out driving around in California. The 3 megawatts, and actually they can get even bigger now. I think there's a 5 or 6 megawatt one for offshore, where your wind turbine blades are, 150 meters long, right? And so those are very, very large, substantial wind turbines. And when you think about wind farms, you're kind of on the similar sort of order of magnitude as those solar farms, right? 100 to 1,000 megawatts, but you might be slightly sort of larger on average for wind farms than solar plants. Okay, natural gas plants. What do you guys think? Any ideas? Yeah, they can get that big, although that would be probably a little bit unusually large for a natural gas plant. You can get as small as in the tens of megawatts for a relatively smaller gas plant. But yeah, we're probably more on the order, maybe on average of like 100 plus megawatts, 100 to a couple hundred megawatts for natural gas plants. Coal plants are going to be similar, but larger in scale generally, so 100 to 1,000 megawatts. 1,000, so at a gigawatt scale, so 1,000 megawatts is a gigawatt. There certainly are a number of coal plants that reach 1 gigawatt, but not a huge number of those, right? Most of those are going to be in the upper couple hundred megawatts. Nuclear plants, so these don't really get smaller than a gigawatt, and we'll talk about why later on. But you can think of these as maybe 1,000 to okay, not 10,000 megawatts, but a couple gigawatts. But we're in that range. Okay, how much power do you guys think California uses at its peak, at the most it ever consumes over the course of like a year? Yeah, so we're kind of around 50-ish gigawatts. Well, it's a little higher than that, and it kind of fluctuates year to year. But the sort of daily peak average is like 25-ish to 30 gigawatts. Okay. Okay, and if you take all of the power plants that are installed across the entire world, how much capacity do you think there is to produce power? If you could all just turn it all on at once. Any ideas? Yeah, about 15,000 gigawatts. Okay? So that's kind of the different scales that we're working with in terms of power. Hopefully we're going to get a lot more familiar with some of this intermediate stuff, but this gives hopefully some context for power consumption in general, and this like order of magnitude estimation thing. So useful to think about that in energy systems. It's going to let you kind of quickly understand things in context, and it's a useful, quick and dirty like fact checker as well. So this is hopefully something that we'll drill down and be able to get good at or better at as the class goes on. Okay, any questions about energy or power? No? Okay. Let's take a quick break. We'll do a 5-minute break, and then we'll come back and we'll talk about energy efficiency. So at 1:05. And in the meantime, if anyone has questions or anything, just let me know. Hey. Hi.
It's nice to see you finally.
Yeah.
And sorry if I'm coughing. I just recovering from a slight cold.
Totally understand. Yeah. Yeah, no problem.
We're still having the meeting on the 8th, correct?
Let me see. I'm pretty sure I have you in my calendar,
Yeah,
but I will just double check. Yeah, at 11.
Oh, and you're in your office?
Yep.
In Gaussy?
Yeah.
Okay.
Do you know where Gaussy is?
Yeah, I've been there. My previous professor, for like my classes he's in Gaussy, so
Okay,
I'm on the
great.
3rd floor, so.
Yep, I'm on the 3rd floor as well. So yeah, come find me on Thursday.
All right, sounds good. Thank
Yeah.
you.
It's kind of hot in here, huh? I remember this room. This was one of the.
I thought Vader was a legend, but this.
Huh?
Can you mess with the thermostat at all?
So the thermostats are all like centrally controlled, actually. Actually, one year that I taught this class, we were in an unusually cold class, and one of the students was working in the office that helps control the temperature, and so he was able to like get in the system and manually bypass something to like turn down the AC.
That was a nice perk.
Yeah, unfortunately, pressing the thermostat here won't do anything.
Oh.
Unfortunate.
Yeah,
Emotional support, I suppose.
yeah.
Yeah. You got a new one for the first one? You okay? Like a break? See the snow? Yeah. You were there for like cold snap. What's your dog's name? Morty.
Morty, what did you bring to class?
He goes everywhere with me.
That's sweet.
He went with me to Florida and to get like certified to the FAA. So he was
So like he flew with you?
yeah,
Like was he with you in the cabin or was it?
yeah. He said in my face the whole time.
Oh, that's so nice.
The only time he was like this was to Seattle when we were taking off and landing. I feel like he wanted to stay, you know, so the window.
Is he like very quiet the whole way?
Just looked at my feet,
That's so sweet.
being attentive.
It's so nice you can bring with him when you're.
It's a good co-pilot. Crazy, right? Long time.
Yes, very popular. Hard to get into.
Oh yeah. Is this your first class in Wellman?
Yes.
Oh yeah.
I've never been here before. Like, I actually like went around. the
Yeah,
front
you have to go
lines.
down to the basement. I forgot where the stairs were, so I actually went around the building too, but let's just go from the outside is the easiest. Yeah.
I couldn't find a restroom when I first came, so I went to the first floor and then I also walked all the way around.
I think there's restrooms.
Yeah, on the other side. I
Yeah,
also had to
yeah,
go
that's right.
around, but yeah, I only found out after I went to the restrooms upstairs and then.
Everyone knows him.
Yeah.
Yeah, I went to Florida.
So this was for this one.
Yeah. It was just that strong one they do. Green one. It was relaxing to get away for a bit. My parents lived in like a retirement.
Yeah, and there's so many of those on that way. Like after like graduation, probably like those retirement.
I mean, everyone, like the entire community is laid out so that you can like anywhere via golf carts.
Yeah.
There's not like normal roads, it's all golf carts. It's like, you know, it's perfect for older people in the sun, you know, you don't need any pressure, great weather, and like, you can go like 60 miles on like a gallon of gas, like on a golf cart.
They just like go off that whole script, that's fine.
Or for one.
So I got my own golf cart, and we were just riding around, checking things out.
And then
My dad golfs.
All right. we're gonna get back into it, everyone. So the last half of the class, we're gonna talk about energy efficiency. So this is an important concept that we'll think about. So energy efficiency is thinking about the reduction in the amount of energy required to provide products and services. So going back to our kind of system diagram here, basically anytime you have an arrow, right, as we can go from primary energy to secondary energy to final energy, we have to think about the concept of efficiency as you convert between different types of materials or energy, right? So when you go from a fuel to electricity, for example, there is some concept of efficiency that we have to think about. So to be careful here, remember in the like conservation of energy, we don't actually lose any energy as we go from one arrow to another, but we do lose what's called useful energy, right? And so if we think of, let's say, heat as a form of energy which is very hard to extract work from, then if I go from a fossil fuel like coal or oil and I convert it into electricity, I convert the chemical energy of that material, like coal or oil, right, in the bonds of those molecules, I convert that into electricity, but also heat. And we think of the heat as energy that's lost, but really it's the useful energy that's lost. And so just keep in mind there that you technically don't lose energy, but for the purposes of what we're talking about in class, right, it's the useful energy that we care about. And the other little nuance here is there's a difference between what we call efficiency versus efficacy. So this is the only time that I'm gonna bring this up and talk about what we're doing as in terms of efficacy. So energy efficiency is strictly defined as a dimensionless number, and it always has to be lower than 1, right? And so the units of your numerator are always the same as your units of your denominator. So efficiency is work or energy output divided by energy input. So technically, a lot of what we're going to be talking about in this class is called efficacy, but I'm just going to call it efficiency, and that's what, broadly speaking, most energy people, transportation people think about is actually efficacy. So this is when you don't kind of have the same ratio of output to input, right? And so efficacy, we're thinking about a service output divided by an energy input. So hopefully that makes sense. So let's say, for example, like a miles per gallon, right? If we convert that into, you can't actually convert that into efficiency because the units are different. And actually, if I were to, does anyone know this? So a mile is a unit of what? Yeah, distance or length, right? And a gallon is a unit of volume. So you could actually cancel out one of the things. So you'd have what would you end up with? Yeah, 1 over area, right? So what would that 1 over area represent? Does anyone know in a miles per gallon? So if I had a car with what we call an efficiency of 30 mpg, and then I just actually canceled off the units, what that number would represent is if you took a gallon of fuel and you stretched it out over 30 miles, what would the cross-sectional area of that fuel be
Oh,
like a
cool.
tube of fuel, right? So it's like a nonsense number, and so efficacy is just a kind of arbitrary way that we've made up to kind of signal a some kind of proxy number to represent something that we can think of in relative terms, but it is not, strictly speaking, an efficiency that like a physicist might think of. Okay? All right.
Your last,
What was that?
I think the second one was supposed to be efficacy.
Yeah.
It
Efficacy.
is other.
Oh, sorry.
Yeah.
Yeah, this should be efficacy. But see, we're already switching to what we're going to be talking about in this class, which is we're going to be replacing efficacy with efficiency. Yeah. Okay, so thermal efficiency. So we can think of, right, efficiency in terms of these units. So worker energy output divided by the energy input. And now, because we're in the efficacy world, we don't necessarily need to make the units kind of the same, right? And so you can have like 100 kilograms of corn that I might use to make a bunch of biofuels, right? And so I might get some ethanol output, right? And so you could have 100 kilograms input, which might be my denominator, and then 11 gallons on the output. And so you could have like 11 over 100 kilograms. And that number in itself is not so meaningful, but you could actually look at other sort of conversion facilities that might have lower or higher numbers, right? And so then from a relative sense, that efficiency number then becomes more meaningful because we're kind of doing a comparison of this ratio across things that are using that same ratio. And so if it's higher, right, then you're saying it's a more efficient process, and if it's lower, it's a less efficient process. You can also do some conversions of your inputs and outputs into units that are a little bit more common, right? And so if you wanted to care more about like the energy content difference in terms of useful energy that you're able to get out of these things, then that allows for like a broader set of comparisons, right? Because now I can compare across things that aren't just like corn and ethanol. You might be able to compare other sort of fuel types, right? So I'm going to standardize these units here. Maybe we say, so corn has an energy density of 18 megajoules per kilogram, whereas ethanol has an energy density of 89 megajoules per gallon. And so I put in 1800 megajoules of energy and I get out 979 megajoules of useful energy. And so my first law efficiency is about 54%. Okay. And this thermal efficiency, right, which is thinking about the efficiency that you get when you discard the like thermal losses, is this 54%, and this particular number will let you compare across other sort of energy conversion metrics. Okay, and so in a very different way, we might think about something like the efficiency, or in a similar way, we might think about the efficiency of like a pipeline, right? So you might have 100 gallons going in on one end, but you might only get 95 gallons out, right? And that's because you're leaking fuel somewhere, right? And so your efficiency is like 95%. Okay, and so again, these efficiencies that we're talking about is mainly about the useful amount of energy that you're getting in as outputs based on some input. we can do this for end uses as well. So this is efficiency of a light bulb. So we think about the electricity input, that might be like 60 watts, right? And so that's the electricity that goes in, and what you get out of it, the energy content of the like lumens of the useful light that you actually use in the service might be something like 3 watts, right? And so you get a much lower efficiency, right? So something like 6% in this particular example. And so what happened to the rest of the energy? Heat, yeah. Right, and so 60-watt light bulb, so that's definitely in reference to like an incandescent, right, which if you guys remember, that uses, that emits a lot of heat energy. A lot of the energy is lost in resistive heat, and so that's why those light bulbs get really hot, and so you get a huge amount of heat emitted or wasted in terms of energy, in terms of useful energy, unless you actually want to get heated, in which case, different conversation. But yeah, so our efficiency of this particular light bulb is quite low.
How do you turn lumens into watts?
Yeah, so there's some kind of conversion that you can do there. I don't actually know the like metrics for doing that conversion, but. Okay, any other questions? So when it comes to thinking about this at the system level, right, efficiency is a useful concept because a lot of the energy conversions that happen in our system are things that we want to reduce, right? If you want to think about sustainability and energy conservation, there's pieces of it which is reduction of the actual services, right, which means that you'll use less energy, but there's also pieces of it that have to do with actually making things more efficient. And that's going to reduce the energy consumption at all that sort of upstream pathways. And I'll show an example of this in a second, and why kind of the light bulb is a particularly kind of like salient example of big gains that you could actually get. And again, we'll talk about this a little bit more in a second. There's kind of another example that a lot of people point to for on the sort of service side, or like the end use services provided side, that folks talk about, say this is kind of like the stereotypical success story of energy efficiency. And one of the nice things about efficiency is you can often think about certain end uses that improve efficiency without having to like sacrifice on the services that it provides, right? And so the refrigerator is, one of these success stories. And so way back in the 1970s, people started thinking about energy conservation and reduction of energy use in general, and trying to improve energy efficiency. That had a lot to do with sort of some of the energy crises that happened in the 70s. And the refrigerator is kind of one of the areas that you can see was kind of like a win-win story. So in terms of the size of the refrigerator, didn't really change much, but the price actually went down sort of in the same way that you were getting energy consumption to decrease. So you're not reducing your service, but you're getting all the benefits of the sort of improvements in energy efficiency. And this is kind of where a lot of end use items would like to be in terms of reducing energy consumption, right? If you can make it cheaper, but also maintain kind of the same level of service, then that's like again, kind of a win-win. So fridges today are like consume maybe like 25% of the energy that they consumed back in the like 1970s. They're astoundingly more efficient than they used to be. All right, any questions about any of this? Okay, at the system level, the things that we think about with efficiency is how we go from one energy pathway to another. Okay, so I mentioned, right, in our system diagram, these different divisions of primary, secondary, and sort of final energy. And so what is that? So think about primary energy is something that you can just go out into nature and kind of collect, right? And so this might be, for renewables, that might be sunlight, wind, and then for fossil fuels, things that you could just dig out of the ground without sort of processing, right? And so crude oil, natural gas, coal, these are all examples of sort of naturally occurring resources that can be extracted from the environment. Some of which are renewable and some of which are not. Secondary energy is when I take primary energy and I process them either through some kind of conversion or modification to become a different sort of form of energy. Oftentimes some kind of energy carrier. So these are like intermediaries between the form of energy in which they're collected and how they're actually delivered and used kind of at the last step, right? And so electricity is an example of this. When we turn like a fossil fuel from that chemical energy into electrical energy, but also any fuel that is refined or processed in any way is a secondary energy. And so the one that we might point to most commonly is like gasoline, right? So gasoline comes from refining of crude oil. And so we consider that to be a secondary energy. You don't just collect gasoline out of the ground without some processing. And then the final delivered energy is the form of the energy at the point in which it's being used to provide some kind of service. And so the final energy is converted into useful energy to meet your energy service, right? And so gasoline might be the final energy form that you have in your vehicle before you convert it into a useful form of energy, or sorry, not useful form of, or into the service that you actually want, which is like being able to move some kind of distance, right? And then like heating or cooling, that's all the actual service that you derive from the electricity final energy at your household. So secondary, what's the difference between secondary and final energy? So if I'm talking, for example, about like electricity, right? What would be the difference between a secondary energy form of electricity versus a final form of electricity? What do you guys think?
Probably cleaner.
Well, so actually, it's not the form of the energy that's different, but the final delivered energy is going to account for the like delivery losses. So you might have like 100 units of secondary energy in electricity, but only like 95 units of that electricity at the final stage. So this does think about losses in the entire system. That's how you would account for that. Yeah, so energy pathways, we start with our energy sources. That's our primary energy. are refined fuels and electricity, secondary, and then useful energy kind of right at the end to provide your sort of services. Okay. So we're gonna talk a little bit more about the importance of this in a second. Well, actually, let me go back here. So, what do you guys think? Is it more important to improve the primary energy, secondary energy, or is it more important to improve the final delivered energy, like the efficiency losses from the providing the services? What do you guys think? Yeah.
I would say it's equally important because you multiply efficiencies, and it doesn't matter where you use it technically.
Okay, so if I were to make a light bulb 5% more efficient, then that's the same as making a coal plant 5% more efficient.
No, you're right, the coal.
Huh?
The coal plant.
So actually, so this might be a little bit counterintuitive. Actually, I'll jump over here real quick. Okay. So this is a schematic that shows kind of the efficiency losses for thermal power energy to produce the amount of energy that you would need for useful lighting. Okay. So we start with 320 units of primary energy. Okay, and so you might think of this as the amount of energy in a stack of coal. We burn that coal and we get a lot of losses, right, because of heat, right? And so when you combust coal, and we'll talk about this in the next lecture, we produce some useful energy in terms of electricity, but we lose about 65% of the useful energy in that fuel to heat, right? And so this might be describing like a coal plant that's like 35% efficient. Okay, so we produce electricity, and then we ship that electricity over to the end use, right? And so it goes through our electricity transmission system and then a distribution system, and you get a little bit of losses. So let's say 5% at each. So starting from 320, we have 112 electricity down to 106 because it goes through the transmission system, down to 101 in the distribution system, and then a little bit of losses locally from resistive heating in your wires at home. Okay, and then we go to our lamp, and so let's say this is an incandescent light bulb, right? And so as we were mentioning before, the incandescents are extremely inefficient. Most of the useful energy is here, right, turning into lumens, but a lot of that electrical energy is lost through resistive heating. So about 98% of that. And so this is what we get here in terms of useful lighting. Okay, so our end goal is to get essentially 1 unit of useful lighting. So there's this question of, should I improve the light bulb or should I improve the coal plants? So we can use this same system and see what happens. Okay, so let's look at the top here. So I'm going to improve my coal plant by 15%. I'm going to make it 35% up to 50% efficient. Maybe I've added a more efficient boiler. Maybe I'm using a slightly more efficient turbine. Okay, and so this number now changes to 50%, back from 35% before. Okay, so at the end, we still want our 1 unit of useful lighting. Okay, and so the amount of coal that we need compared to before was 320, and now because I've improved the coal plant by 15%, I only need 224 units of coal. Now let's change our light bulb efficiency from 2% to 10%. So instead of a 15% improvement in power plant efficiency, I have an 8% improvement in the light bulb itself. And so this would be more like, not from an incandescent to an LED, this might be more like an incandescent to like a CFL. Okay. Okay, and so here, these losses, instead of 98%, it's 90% here. And so you can actually work backwards what you would need. And it turns out, right, you would only need 64 units of coal with all the same efficiencies in the system before. And that's because it's not the same, because your efficiency gains are magnified to every upstream efficiency loss, right? So that 8% improvement means every stage essentially gets to see that improvement. So it affects all the upstream stuff, but not the downstream stuff. So technically speaking, right, this improvements closer to the service end magnify your efficiency improvements in the system. So that can be a little bit sort of counterintuitive. But is it better, so then going back to my original question, is it better to improve the light bulb or the power plant? Well, maybe according to this, you might say kind of the light bulb, right? But it's not always so clear cut. There are kind of pros and cons to both. So the final to service, so reduces the amount of energy needed at each upstream stage, as we just demonstrated, right? And so to get that 1 unit of light energy that I need, I get less mining and oil extraction, I get fewer power plants, fewer pipelines, and lower energy losses across that entire chain. But improvements in the primary to secondary efficiencies, so things like improving the power plant, might be easier, right? So it can be centrally implemented, and so energy companies are more rational, we'll call it rational actors than individual consumers. And so is it easier to convince the entire population of the country to switch light bulbs, or is it easier to get a handful of power plants to like upgrade their, their equipment, right? And so this is just to point out that it's not so simple of an answer to think about when we're actually trying to implement these types of things. But maybe counterintuitively, right, that some of those service improvements can actually make really big difference. And so, I was pointing to this earlier example of this light bulb, right? And we had this big transition away from incandescence, 10, 15 years ago, and that actually can lead to, pretty big gains on the sort of upstream, more than you might think. Okay, any questions about that? So the way that we calculate efficiency of a system across its entire across the entire system is that you are sort of multiplying efficiencies throughout, and so the total efficiency of your entire energy pathway looks something like this, where the thermodynamic efficiency of each given set in the pathway can be sort of multiplied across your primary, secondary, and final stages. So,
in your previous example, though, that wouldn't account for upgrading the the factory where those the newer light bulbs were being made though, right? Like that wouldn't,
No.
that wouldn't account for that type of upstream modification in its efficiency, or like even just distributing that many light bulbs to the entire population.
Yeah, that's right. So that would that would be talking more in kind of like a life cycle basis. You can do that in these schemes, but it's about kind of where you're drawing your sort of system boundaries. Yeah. Okay. So in these particular examples, so this is like a table going from primary energy to some kind of useful energy at the end. We have primary energy, secondary energy, final energy, and then the sort of useful, right? And so that maybe this is like a light bulb or something, or probably not a light bulb, but some other service thing that uses the electricity input pretty efficiently. But these are different pathways, right? So I might go from coal, process that to the electric plant, convert that into electricity. Your biggest loss going from here to here is the thermal piece, and then transmitting to its end use, and then how it actually gets used. And we can calculate, right, the efficiency like so. So in every step, we're just taking the ratio of the input versus output energy. So that's our input into the coal processing. And so maybe you lose a little bit of energy there, so it's 99% efficient there. And again, as that coal gets input into the plant, maybe you have a little bit of losses there, but again, it's like 90% efficient. The biggest loss is going to be here, 0.89 to 0.28. That's the thermal losses from actually combusting the fuel and turning it into electricity. So in this case, you have a 31.5% efficient coal plant. So the electricity from the output of the plant going to, in this case, a manufacturing facility, you lose something like 10% of electricity there. And then in the final step, whatever this thing is doing in terms of the actual usage of the electricity into its service is 72% efficient. And if you multiply all of these efficiencies out, so 1 times 0.99 times 0.899 times 0.315 times 0.893 times 0.72, you'll get about this number at the end, which is our final pathway efficiency, right? And that is just the ratio between our initial start and the final output. And so what's the point of doing all of this if I already know here and here? This means that I can break down like intermediate efficiencies within this kind of pathway, right? And so if I want to know the efficiency of, going from coal to or electricity generated from coal to the manufacturing plants, or any other arbitrary pieces of that path, you can do so. And it also means that if you know the efficiencies of the intermediate steps, that you could calculate the total final efficiency, right? So if you didn't have these numbers, but you had these numbers, you could calculate that final efficiency. So that's the relationship between your efficiency paths and your sort of final efficiency number. Any questions? Yeah.
How come in the larger chart the output from the coal processing or the natural gas refinery is considered primary, where the output from the
So everything primary here should be, so we're gonna start with primary energy that is like stuff that can be collected materially from anywhere, right? The point at which you become secondary is when you convert whatever this is into a different form of energy. The reason why you've got a couple of steps here that are still in the primary energy piece of it is because this is something like taking the coal from like point A to point B, and then you like lose some of that. But the actual form of the energy hasn't changed, if that makes sense. And then the moment I change the energy, it goes into this box here, or this color, right? So these are both when I combust coal or combust natural gas, then they become electricity going through the turbine. Technically speaking, I guess it's gonna turn into like, technically there's an intermediate step where it's mechanical and kinetic energy, because you're like steam moving a turbine to generate the electricity. They don't, I guess that's not included in here. We kind of think of that happening kind of instantaneously. For crude oil, this is once it hits the crude refinery and gets converted into whatever thing that needs to get used. So this might be like diesel or gasoline. And then, okay, it's gasoline because here it says delivered to petroleum at service station. So to convert from that crude oil into gasoline, you lose like 9%. That gasoline gets shipped to like a gas station, but you don't have high enough losses to even see that difference here. Does that make sense?
Yeah, I think so. It's
Yeah.
like the crude refinery is kind of a form change than the refinery.
Yeah, that's right. So basically, whatever form it's in at the beginning, once it changes form, then you're in this territory here. Yeah. Questions? So one last example, you could look at something like a gas car versus an electric car. Yeah, so I often hear that like electric cars are way more efficient than gas cars, which is a true statement, and even holistically it is true. But I always feel a little bit unfair about that claim, oftentimes because to me it feels like they're talking very sort of apples to oranges in terms of the efficiency comparison, right? So with a gas car, you take some kind of fuel, and then we start with crude oil, we turn it into gasoline, the gasoline gets combusted in the engine, and then that gets converted into motion to provide the service, right? And the combustion of the fuel is where you lose the most energy, right? So here, it's 7.58 exajoules going to 1 exajoule here. So you lose a lot of energy in the combustion of gasoline into heat inside of your engine. And so we say, oh, like a gas car might only be like 15 to 20% efficient. And someone would say, well, an electric car is like 90+% efficient. Actually, we can't even see that here because it's the charge point, not the conversion of the battery energy into motion. But actually, that electricity comes from it might be coming from like solar or wind, in which case, you know, it would be clean. But it might also be coming from a fossil fuel that is getting combusted and then turning into electricity. And it just so happens that that's like happening outside of the engine, right? And so that's the point at which you get the most losses. And we see that here, 8.96 to 2.82. And it just so happens that that's the point. That point is outside of the car, and so we don't count that, right? But if you were to count the whole thing, that the whole sort of energy conversion system, then you can do I would say a more fair comparison of the efficiencies. In which case, EVs are still a lot more efficient, right? We're saying 39% compared to 13%, but it's not like a 90+% compared to like a 15% number. So, yeah, just things to think about as you get comfortable and familiar with some of these skills. And so, all of this efficiency stuff is going to be really important for us to think about how energy is moving and converting between all of these pieces of our energy system. And hopefully a lot of this will become kind of second nature to you guys as we move through the class.
It's also kind of temperature agnostic, right? Because wouldn't, like an ice engine improve in efficiency if it was slightly colder than
Yeah, I think
vehicle?
these particular numbers are kind of derived empirically just based on actual numbers that are observed, and so any individual vehicle that's going through this process might have slightly different numbers depending on things like ambient conditions, but also on like things like how hard you step on your gas pedal or whatnot, right? But this is kind of in the aggregate what that efficiency is going to look like. It's sort of kind of inherently accounting for all of those things in each of these transition periods. Yeah.
But if you consider like from the start of the primary energy, doesn't the electric vehicle sound like way less efficient?
Yeah, it does. But that's like, that's a product of the system thinking, right? And so it's not necessarily that the EV is less efficient. It is some parts of that entire system pathway is not as efficient, right? And so it'll maybe it'll make it look a little worse kind of at the end, but it is a realistic examination of really how much energy that we use at how much energy at the start that we need to get what we want out at the end point. Yeah. Cool. Okay. Anything else? Any other questions about any of this? Okay. So that's it for today then. Yeah, we'll see you guys on Wednesday. We'll start talking about some of the specific power generation for electricity on Wednesday. And yeah, remember next week it'll be recorded lectures.
I have a question. So every second Wednesday from 1 to 2 o'clock, I usually have. I'm part of this resources for the Futures Critical Minerals Lab.
Okay.
Every second Wednesday we have from 1 to 2 like a meeting